Hello, in this video we're going to go over problem set 6 and how to solve each problem in depth. So let's start with question number 1. To determine the degrees of unsaturation, then draw the structure of compound A based on its formula in proton NMR. And we're given the integrations of 5 to 1 from left to right. So the first thing I would do here is to label everything. That's going to be extremely helpful. So we're going to label each peak as 5, 2, and 1. So it's asking us to find the degrees of unsaturation, and if you remember the formula for that, we're going to look at the carbons and hydrogens, and in this case it's going to be 7 minus 1/2 of the hydrogens, which is 8 plus 1, and that should yield degrees of unsaturation of 4. Whenever you see degrees of unsaturation of 4 or greater, that should automatically jump out to you that, hey, we're probably working with something aromatic like a benzene or something. So I'm just going to draw that out here just for our reference. So now let's look at the integration table. I always recommend making one of these when reasoning through these types of problems, especially with proton NMR. It can really help organize your thoughts. So let's see now at around 2.4 we have an integration of 1. At around 4.5 we have an integration of 2. And at around 7.2 we have an integration of 5. So now we have to pause and take a look. Do our integrations match up with the number of hydrogens? And we have 1 hydrogen here, 2 here, and 5 here, which all makes sense. Now, and in this case, it's time to propose some reasonable structures here. So immediately right off the bat, these 5 hydrogens, I can automatically assume that this is going to be part of the benzene. Whenever you see peaks at around 7 or 7.5, 7 to 7.5, with something like an integration of 5, that is likely going to be a benzene if there should be one. All right, so now let's look at the 2 hydrogen ones, and the most likely structure for that is going to be this CH2. And now for the 1H, we're given in the formula that there is an oxygen in there somewhere. So it is likely that this is going to be an alcohol. Even though it doesn't tell us that there's an alcohol, we can assume that it's an alcohol based on a process of elimination. And now it's time to determine whether these are end pieces or mid pieces. So for the OH, this has to be an end piece. Can't really go anywhere else. The CH2 is a mid piece, and the benzene is an end piece. So now it's time to fit these pieces together, and there's only a certain number of ways we can fit this all together. It's going to have your benzene here, and we're going to have a CH2, and since CH2 is a mid piece, the alcohol must come off the CH2. So this is your final structure for number 1. Let's look at number 2. Determine the degrees of saturation, then draw the structure of compound B based on its formula and proton NMR, and right here, very important information, the IR spectrum shows a strong signal at 1720. Right immediately, that should jump out to you that this is a carbonyl group. So if we look at our compound, we have our C6H12O. We can kind of already know that the C-double-bond-O is going to count for this oxygen, and there probably isn't going to be an alcohol anywhere in here. All right, so now let's look at the degrees of saturation. If we do the equation, it's going to be 6 minus 1/2 of 12 plus 1 to give a degree of unsaturation of 1. And remember, that means there could only be one double bond or one ring somewhere in the structure. And since we already know that there is a C-double-bond-O from this IR spectrum showing a peak at 1725, that is already accounted for. So we don't need to worry about any other rings or double bonds and all that kind of stuff. So now it's time to make an integration table. Let's look at the various peaks. So initially we have a peak at around 1.2, and the integration is 1 to 3 from left to right. I should have labeled that immediately, that is my bad. Integration of 3 and integration of 2.1, let's call it, with an integration of 1. Now let's pause and ask ourselves, does our number of integrations match up with the number of hydrogens? And the answer here is no. We have 4 hydrogens in our integration, while we have a total of 12 hydrogens in our compound. So we must multiply everything by a factor in order to scale up, because the machine is giving us the simplest formula. So in this case, the common factor to get us to the correct number of hydrogens is going to be 3. This is going to give us 9 hydrogens and 3 hydrogens here. And now this is starting to make a lot more sense. So now it's time to propose a structure. Whenever we see an integration of 9 hydrogens, that should immediately jump out to you that we have this group right here, this terbidyl group. And for the 3 hydrogens, that should immediately jump out to you that that is going to be a methyl group. All right, so now let's label this as end pieces or mid pieces, and both of these are going to be end pieces. Okay, so now let's try to piece these all together. There's only a certain number of ways we can fit everything together. Remember, we also have this carbonyl group here, and once you do enough guessing and checking, it doesn't really take long. You're going to find that your structure looks something like this. Okay? Cool. Now let's go to question number 3. This one was quite tricky, so let's go over this one. Determine the degrees of saturation, then draw the structure of compound C based on its formula and proton NMR. Hint, the IR spectrum shows no peak near 1720. No peak. So that means C double bond O group is not going to be present. All right? And if we look at our compounds, we see that, okay, we have an oxygen in here. So immediately what I would think is maybe there's an alcohol or something like that, but we don't necessarily know that yet. We need to look at our proton NMR. So let's first deal with the degrees of unsaturation. Our equation is going to be 3 minus 1/2 of the hydrogens, 6 plus 1, degree of unsaturation of 1. So that tells us that somewhere in our structure is a double bond or a ring. Okay, so now let's look at the proton NMR. Integrations of peak 2 to 1 from left to right, so 2 and 1. So now it's time to make our integration table. And starting off, we have a signal at 2.7 with an integration of 1, and a signal at around 4.7 with an integration of 2. Now let's pause and ask ourselves, does our number of hydrogen integrations match up with the molecular formula? And in this case, it does not. So just like the previous question, we need to multiply everything by a common ratio to reach our molecular formula, and in this case, that ratio is going to be 2. And this is going to give us 2 hydrogens here, 4 hydrogens here. So now let's ask ourselves, propose a reasonable structures for these groups. So for the 2 hydrogens here, the most reasonable one, we've seen this a bunch of times, is going to be a CH2. I'm going to go ahead and immediately label that as a mid piece. And for the 4H, there can be many different things, but the most likely things, remember, think of the most obvious things that jump out to you. It's just going to be 2 CH2 groups, and this is going to be a mid piece, or mid pieces. So remember, we also have an oxygen in here somewhere. So right now, a lot of students here got stuck because they're wondering, we have a bunch of mid pieces and no end pieces, and they kind of stuck because they haven't really seen this kind of thing before. But remember, a degree of unsaturation of 1 means that you can have a double bond or a ring structure. So, and in this case, you're going to have a 4-membered ring that looks something like this. So this is going to be kind of confusing, but it's okay. We can double check our answers by using spin-spin coupling, basically looking at the number of peaks that the proton NMR gives us. So we can label this mid piece here as A. We can label this one as B. And if we go over to our structure, the mid piece here, this is going to be A, and this is going to be B and B. Remember, there's a plane of symmetry in this molecule, so the B's are going to be the same. And I'm going to draw the hydrogens out here just for visual purposes and convenience. So let's check the spin-spin coupling. Let's look at this first row. At the integration of 2.7, there's the mid piece A. So let's look at 2.7 right here. Let's count the number of peaks. 1, 2, 3, 4, 5. It's going to be 5 peaks. If we look at A, the n+1 rule states that if there are 5 peaks, there should be 4 surrounding carbons, or there should be carbons surrounding the carbon of interest with 4 hydrogens total. So if we look at A, if we look both left and right at its neighbors, we have 2 hydrogens here, 1, 2, and 2 hydrogens here, 1, 2, which gives us a total groups of 4 hydrogens, which makes sense because according to the n+1 rule, there should be 1 more on the peak, and there are 5 peaks here for A. So that checks out. Now let's look at B. So for B, let's count the number of peaks. 1, 2, 3. So since there are 3 peaks, that should tell us that the neighboring carbons should have 1 less than the number of peaks of hydrogens. So in this case, there should be 2 hydrogens. So if we look at B carbon, I'm going to erase these arrows for the A carbon. If we look at the B carbon, the neighboring here is an oxygen, doesn't have any hydrogens, we can't really count that. If we look at the one down here, there's going to be 2 hydrogens, 1, 2. And according to the n+1 rule, it's going to be 2 plus 1 for a total of 3 peaks. So remember, the spin-spin coupling is a good way to double check and make sure your structure matches up with the formula and the proton NMR. So let's look at question number 4 now. This goes back all the way from exam 1, but this is still extremely relevant. So we have a benzene, and we're going to chlorinate it. And this is very simple. We're just going to add a chlorine here on our benzene. And now it's important to remember that now our benzene has a chlorine on it, and we need to add a HNO3 and H2SO4. And it's important to know that chlorine is going to be an orthopara director. If you remember where those positions go, it's going to go here and here. And in this case, the most prevalent species of the product is going to be the ortho position, and the minor species is going to be the para position. And now we're taking this reactant and reacting with NaOCH3, and if you remember, plus heat. And if you remember this reaction, this is an aromatic nucleophilic substitution reaction, or our SNAR reaction. And all this is going to do is replace the chlorine up here with this methoxy type group. Okay, so this is going to be your answer for question number 4. Now let's look at question number 5. Propose a synthetic pathway for the following molecules starting from unsubstituted benzene. Remember, this is still going back to exam 1 type material, and there are multiple different ways to go about this that I've seen. People have been using Grignards, people have been using Friedel-Crafts. It kind of is up to you guys. As long as it works and you guys are obeying all the rules, then as long as you get to the final product, it doesn't really matter what path you take. It's not about the journey, it's about the destination. Okay, so let's start here. I'm going to go ahead and react this with this Friedel-Crafts. And what that's going to do is add this group right here. And now the next step, we want to get this group right here to look like a carboxylic acid. So in order to do that, the most convenient way, in my opinion, here I'll re-add the highlights actually. I'll say we want this, is we want to reduce this with H2PD on C, and what that's going to do is turn this into just a 2-carbon chain coming off of the benzene. And in order to turn this into a carboxylic acid, remember we can oxidize this. As long as we have free-floating hydrogens attached to these carbons, this reaction can occur. If there are no hydrogens, then this reaction is not going to occur. So the reagent for this one is H2CrO4 plus heat, and that's going to turn this, or any however long carbon chain, into a carboxylic acid. And now we know that this is a strong meta-director, right? Remember in the previous videos that I've mentioned, there's a lot of resonance going on over here. So it's kind of fighting the benzene, and it's kind of drawing these electrons out. And it doesn't ask you for like resonance or anything like that, but if we want to, we can justify this meta direction by resonance. And what I'm going to do is I'm going to add a nitro group because eventually we want to get to this alcohol group. And it says here you only have one method of placing OH directly on a benzene ring. So we kind of already know we want the nitro group somewhere on there. So we're going to end up with something like this. Okay, and the next step I would do is we want to ultimately turn this into an, we want to use one of our diazonium salt reactions, right? So we want to turn this, we're going to reduce this with H2, PD on C, one of my favorite reactions because it's the GOAT. We're going to turn this, and this is going to reduce the NO2 into, or NO2 into NH2. And this carboxylic acid remains. And now this is going to be our HONO reaction, or NaNO2 HCl 0 degrees Celsius, and that's going to be our diazonium salt reaction. My handwriting is getting very bad, I apologize for that. And that's going to turn this into N triple bond N with a plus here, and remember we had the HCl, this is just going to turn into like a spectator ion, nothing of our concern. And finally, we could turn this into an alcohol group by using a little bit of H3O plus and heat. And that is going to turn that into an alcohol. And that is going to be our final product. So if you guys are a little confused of how I got from point A to point B to point C, a very useful tactic is retrosynthesis, basically working backwards. So for example, if you know that this is the product, right? There's only one way you know how to get to here. And let's say you don't know where to start. You know that like H3O plus is the only way to get to this OH on the benzene ring, and you know this comes from this diazonium salt. And then from there, you can work back and be like, okay, I know what forms this reagent. It's going to be the HONO reaction. And then you can start working backwards and working backwards. And if you want to, you can also start working forwards and working forwards. But it just goes to show you that you can either work forward or backward. And as long as you get to the right product, it doesn't really matter how you get there. Cool. I'm going to label this as retrosynth. Okay, awesome. Now let's go to question number 6. Use the provided spectra on page 4 onward to determine each structure. So we have compound letter A. Let's start here. So we're given a combined spec problem. We're given some percentages of some atoms, an IR, proton, and carbon NMR. So remember the first thing I said, if you watch my How to Excel at Combined Spec video, as I'll link right here, the first thing you want to do is get a molecular formula, and that can either be provided to you, given to you in a mass to charge ratio, or it can be more annoying like this, and you have to calculate it out. Can't use the rule of 13, but that's okay. This is also very important and very useful. So we're going to start out by writing our percentages. We're going to write them as masses. 7.34 grams of hydrogen. And remember, the jingle that I kept preaching in my past however many videos, percent to mass, mass to moles, divide by small, multiply to a whole. So we kind of already have the percentages, and we're doing percent to mass, and that's going to be this first step here. We have the masses of grams, we have the mass of hydrogen, we have mass of carbon, and if we look at the remaining, we want to assume that there's a total mass of 100. So this remaining is just going to be 52.9 grams of X. We don't know what that is. So remember the next part of the jingle, percent to mass, and then it goes from mass to moles. So this is just going to be a look at the periodic table. Do you know how to do this from Gen Chem? And here we don't know the mass, so I'm just going to put mg mole of X. So we have percent to mass, mass to moles, divide by small. I did not calculate this out. Okay, this is going to be 3.31. This is going to be 7.27. And this is going to be 52.9 because we don't know what it is. Next part is going to be divide by small. I'm going to go in purple. The smallest one is going to be 3.31. And after we divide by small, we're given 1 here, we're given 2.2 here, and we're given, let's say, 16 here, something like that. And the last part of the jingle is multiply to a whole. So we want to multiply all of these values until we get a whole number, and I guess the only thing we want to look for is this 2.2. We want to make that a whole number. And once we do the math out, we find that 5 is going to be the lowest common factor to give us our molar ratio. This is going to be 5, this is going to be 11, and this is going to be around 79.9. And now we know the mass of this unknown compound. If we look at the periodic table, this is going to be bromine. So now we have a molecular formula to work with. We have C5H11Br. Okay? So that makes our life a whole lot easier. And the question's asking us for the molecular formula, degrees of unsaturation, and the structure. So now that we have the molecular formula, we can find the degrees of unsaturation. And now we have a halogen. We need to be careful about that now. That is to be accounted for, unlike oxygen. Do not account for oxygen. Only halogens and nitrogens. Well, and carbons and hydrogens, of course. So, finding the degrees of unsaturation, it's going to be 5 minus 1/2 the number of hydrogens. And it's going to be minus 1/2 the number of halogens. Plus 1. And this should give you degrees of unsaturation of 0. So what does that tell you? Well, it tells you that there are no double bonds and there are no rings. So we can likely assume that we just have some straight carbon chain with a bromine somewhere here in our structure. Now let's take a look at the IR spectra. First thing, any red flags jumping out? I don't see anything of importance. We don't see anything around 1720. That means there's no C double bond O. We don't see this massive alcohol stretch. We don't see anything like that. I don't see any strong C single bond O stretch here. Nothing there. There isn't really many overtones or out of plane bending, so it can't be aromatic, and we also know it's not aromatic because degrees of unsaturation is it's 0, so we can't have anything. So the IR spectra, kind of useless, not gonna lie. That's okay, we can move on to the... Actually, I take that back. It's not useless. It tells us what isn't there. Okay, now let's go on to the proton NMR. And remember, I preach, make this chart. It's going to make your life a whole lot easier. So thankfully, we already have the integrations given out to us, but let's still make the chart anyway. So we have around 0.9 integration of 6, 1.7 integration of 1, 1.8 integration of 2, 3.4 integration of 2. Now let's pause. Does our number of integration hydrogens match up with the molecular formula? And if we add them all together, we get 11. And in our molecular formula, we have 11 hydrogens. So cool, that everything makes sense. Now it's time to propose a reasonable structure for each one of these groups, starting with 6 hydrogens. The most reasonable structure here is going to be 2 N pieces, 2 methyl groups. And once you start doing this enough, you'll start picking up that, okay, so whenever we see something at 0.9, it's typically going to be a methyl group of some sort. Whenever we see something at 7, it's going to be something aromatic of some sort. And that just comes with practice. Cool. Now let's look at the next one. We have 1 hydrogen here. We don't have any alcohols. We just have straight carbon chains. So we can assume that it's something looking like this. And this is going to be a mid-piece. Now let's look at the 2 hydrogens down here. And thankfully, with all of our previous information, we can deduce that these are going to be 2 mid-pieces looking like this. I'm going to label this as A, B, C, and D. Okay, so now we have, don't forget the bromine as well. We can't forget about that. We have all this good stuff. Now let's look at our carbon NMR. Remember, the carbon NMR doesn't really tell you that much, in my opinion, but it does tell you a very important thing, that if you have a plane of symmetry or not. So remember, the rule goes, if you have fewer carbons than the or fewer carbon peaks on the carbon NMR when compared to the molecular formula, you have a plane of symmetry. So if we look at the peaks, 1, 2, 3, 4 peaks, molecular formula, we have C5. So since there are fewer peaks than molecular formula equals a plane of symmetry somewhere. The machine can only detect 4 unique carbons. There's a plane of symmetry and 2 carbons are chemically equivalent. So we have all that information and we can try to assemble a structure here. So I would start with the end pieces because that makes the most sense. And since they are chemically equivalent, they're going to come from the same neighboring carbon. And now if we look at the next couple of pieces we can attach here, we have B, C, and D, which are all mid pieces. But in this case, B is the only one that makes sense, because if we try to add C and D here, our structure dies. It's a dead end. We can't really add anything. So let's add B here, CH group, and that continues on. And logically, the only things that can come next are 2 more of the CH groups and then a bromine. Cool. Now let's label these. Remember we labeled them as A, B, C, D. Let's label these. These are both going to be A. Let's label this as B. Let's label this as C and D. And on our chart as well, we can label this A, B, C, and this one, it's a whole lot of mess, but we're going to label that as D. Okay, so now we have a preliminary structure. We have a plane of symmetry. So we're kind of all on the right track. Now let's double check our work. And we must do that by spin-spin coupling. So let's look at A. A on this peak has showing a doublet. So what does that tell you? A doublet basically means that the neighboring carbons only has 1 hydrogen. There's 1 fewer hydrogen than the number of peaks. There's 2 peaks here. If we look at A, neighboring carbons with hydrogens, sure enough, we only have 1 hydrogen. So that makes sense, M+1 rule. Now let's look at B. B, it says here, this peak is a combination of a quartet on the left and an M9 on the right. So an M9 basically means that there is 9 peaks. According to the N+1 rule, there should be 1 fewer number of neighboring hydrogens, so there should be 8 neighboring hydrogens. I'm going to go ahead and erase all this good stuff. And if we look at the B hydrogen, if you look at the B hydrogen, the neighboring carbons, there's going to be 3 up here, 3 hydrogens down here, 2 hydrogens here, for a total of 1, 2, 3, 4, 5, 6, 7, 8 plus 1, because it's an M9. So that makes sense. And if we look at both C and D, let's look at C first. C is going to be a quartet. That's what it says right here. So if you look at C, let's look at its neighbors. Its neighbors directly to its left and right. To its right, D, 2 hydrogens. To its left, 1 hydrogen, for a total of 3 hydrogens. N+1 rule says there should be 1 more. So it's going to be 4, and that tells you the number of peaks. And surely enough, the question says that it's a quartet. Cool. So now, I guess by process of elimination, we just know that D has to be in the right spot because we've already ruled out everything else. And if you are having a little difficulties, remember that D is also way far down at the integration of around 3.4, while everything else is around 2. And that is due to the fact that it is really close to that electron withdrawing bromine there. Okay? So let's go over compound B. I'm not going to draw out the answers over here in the answer thing. I'm just going to work over here on the spectra themselves. So this is the answer. Okay, let's look at compound B. Thankfully, we're given a molecular weight, so we don't need to do a lot of that math. And I'm going to take a different approach here. It's useful to have multiple tricks in your toolbox. So one of the tricks is using the rule of 13. What that basically says, you take the molecular weight, divide it by 13, and you should get a decimal. In this case, you get 8.77 whatever. Well, you want to look at this whole number. That whole number is going to tell you the number of carbons in your molecule. So you know this is going to be C8H something. We don't know. and it's going to be 8 plus something, right? So the trick here is once you have that, this plus looks very bad. Once you have that, you want to re-multiply 8 by 13. And once you multiply 8 times 13, you get 104. And then you want to take the difference between 114 and 104, and that gives you 10. And basically you want to add that 10 onto that 8, and that should give you molecular formula C8H18. Cool. And we can double check that as well because we're given these percentages, and that principle can be seen in compound A, the math, so I won't be doing that again. So now we have the molecular formula. Awesome. We can find the degrees of unsaturation. 8 minus 1/2, 18, plus 1. That's going to give degrees of unsaturation of 0. That tells you there's going to be no double bonds, no pi structure anywhere. So we're just going to have a straight carbon chain. Hydrocarbon chain, my apologies. So now let's look at the IR spectra. Anything jump out at you? I don't see anything that jumps out at me. No alcohol, no C double bond O anywhere, no C single bond O, no overtones, no out of plane bending, no major peaks to the left of 3000. Useless. Or I guess I said this literally in the last question. It's not useless. It tells us what's not there. Okay, cool. Now let's look at the proton NMR. Let's draw our chart out, our little t-table, and let's go down the line. At 0.9, we have integration of 9. We've seen this a bunch of times before. What does an integration of around 0.9 typically mean? I can't hear you, but if you said something like there's methyl groups there, you'd be correct. So I'm not even going to bother drawing everything out. I'm just going to go ahead and automatically... Actually, no, I won't do that. That's bad practice. Okay, now at around 0.95, there's integration of 6 hydrogens. And since it's also in that similar region, it's likely to assume that there's methyl groups down there. At around 1.1, there's going to be 2 hydrogens. This can't be a methyl group. This is probably going to be a mid piece, but let's get to that later. And around 1.7, we have an integration of 1 hydrogen. So that's probably going to be something like a mid piece as well because we have no hydrogens on alcohols to account for. So now let's propose a reasonable structure after we pause. Let's add up the number of hydrogens. Do they add up to the number of hydrogens on our formula? And I get a total of 18. And remember, we have C8H18. So that makes sense. Now let's propose some structures. As I said before, whenever you see 9 hydrogens at around 0.9, it is highly likely that this is going to be your structure. The 6 hydrogens here is highly likely that this is going to be your structure, these 2 methyl groups. For anything that has 2 hydrogens, it's likely to be a mid-piece CH2. For 1 hydrogen, it's going to be CH. Let's label this. This is going to be N-piece. It can't be anything else. These are N-pieces. They can't be anything else. And these are both mid-pieces. Cool. Now that we have all that situated, we can start to assemble a structure. I'm going to label this as A, B, C, and D. And I'm going to label the chart as well. This is going to be A, B, C, and D. Perfect. Now, let's look at our proton NMR before we continue. How many peaks do you guys see? I see a total of 1, 2, 3, 4, 5. Remember, 5 peaks is less than the number in our molecular formula of 8. So what does that tell you? That should scream you have a plane of symmetry somewhere in your molecule. So now let's try to assemble this puzzle. So let's start here with the N piece. We know that's going to be somewhere. Let's just put that down because that's a good place to work from. You have our N piece. Okay, and now we have to try to figure out, do we have well, it can't be B that's next here. B cannot be there because the structure will end. So it can either be C or it could be D. In this case, we don't really know, which is quite unfortunate. So you might have to do some guessing and checking. And eventually, this is why spin-spin coupling is so important. So it's also of note here that we have two equivalent methyl groups right here. And those, since they are equivalent, they must come from the same carbon, right? So now let's think about this. These two are chemically equivalent. Now we just need to figure out what goes where. Does C go next to this terpetal group, or does D go next to this terpetal group? Let's think about this logically. If we try to put the mid-piece C onto these two equivalent methyl groups, the structure dies, right? So that doesn't really make sense. So the CH group has to go there, which leaves only the CH2 group going here. I didn't really have to even guess and check that much. Once you can kind of just logically deduce where everything's going to go based on the structures that you've proposed up here at your T table. That's why this chart is so incredibly important. So now we can double check our work with spin-spin coupling. So let's take a look. Let's label these guys. This whole group is going to be A. These guys are going to be B. This is going to be C, and this is going to be D. Let's look at A first. A, singlet. Let's look at A is going to be singlet. So these protons here, sorry. Let's look at the neighboring carbon. The neighboring carbon, this is the only neighboring carbon. Surely enough, it has 0 hydrogens. N+1 rule, 0 + 1 gives a peak of a singlet. So that makes sense. Let's look at letter B now. Integration of 0.95. Going to be right here. That's going to be a singlet as well. Is that a singlet? This is going to be a little bit tricky in the fact that we should see here, this is why spin-spin coupling is so important. It caught me a little off guard. We have the 2 hydrogens here, and if we look at the neighbors, there's only a carbon here with 1 hydrogen. According to the N+1 rule, we should have a doublet, but in this case, we only have a singlet. So it might be a little confusing of why this doesn't exactly match up, but we can skip that for now and look at the next couple of structures. So let's look at letter C now. C here on the chart, there's 2 peaks. That's a doublet. Let's look at C. Let's look at its neighbors. 1 here. There's no hydrogens here. Let's look to the left. There's 1 hydrogen here, and that's a doublet. So that makes sense. There's a doublet here, so C makes sense. It's just B that's a little wonky. Now let's go to D. D has, let's look at the number of, first let's look at D here, right? This proton. I'm going to go this in red. Let's look at actually I'm going to draw this hydrogen right here for simplicity. Let's look at this guy's neighbors. We have 3 up here, 3 over here, 2 over here. That's 3 plus 3 is 6, plus 2 is 8. And remember, it's N+1. Don't forget about that. So we should see something like 9 peaks. If we look over here, 1, 2, 3, 4, 5, 6, 7, maybe like 8, 9. It's kind of hard to tell, especially with this proton NMR stuff, because after all, this is experimentally done and nothing is perfect in an ideal world. But given everything else, given that A and C do make sense, and given that D has a very, very close to number 9 peaks matching with the spin-spin coupling, even though B is kind of confusing, everything else makes sense just by probability and process of elimination. Okay, last question. Question C, compound C. So now we have a molecular weight, and we're given percentages of carbons and hydrogens as well. I'm going to go with the rule of 13, just for the sake of time. And if we divide this out, we should get 6.77. And remember, we're looking at this whole number. So we should get C6H, let's say 6 plus whatever, 6 plus N. And now the next step is to multiply 13 and 6. And if we multiply that, we get 78. And if we take the difference between 88 minus 78, we get 10. So if we add 10 into here, the molecular formula should be C6H16. Does this make sense? If you said yes, unfortunately you'd be incorrect in the fact that if we look down here, the percentages do not add up to 100. So there is something else here that we don't necessarily know what it is. We could go through and work out all the math, but there's a little shortcut. If we use the periodic table, we can kind of deduce what is going on here. We could have a halogen or something like that, but if we immediately look at our IR spectra, we jump out immediately. What jumps out? This fat OH stretch. That tells us we have an oxygen somewhere in our molecule. So just by deductive reasoning, we can probably assume that there's an oxygen in here. And oxygen, according to the P table, has a mass of around 16, while carbon has a mass of around 12, and hydrogen has a mass of around 1. A short and dirty way to deduce the molecular formula is by taking the difference of carbons and hydrogens and replacing them with the equivalent masses of oxygens. So what do I mean by that? We know that there's going to be an oxygen somewhere in here. So we want to subtract a carbon, and we're going to subtract 4 hydrogens. And that's going to be minus a molecular weight of 12 minus a molecular weight of 4. And that, if we subtract that out, we're going to, at the same time, we're going to add 1 oxygen, because oxygen has a molecular weight of 16. So we can't create or destroy masses. They can only be transferred, and therefore this equivalent mass is going to give us a final formula of C5H15, my apologies, minus 4, H12O. This is likely going to be your structure. Now let's find the degrees of saturation. Du is equal to 5 minus 1/2 of 12 plus 1. Remember, we don't account for the oxygen here. So once we work this math out, this should give us degrees of saturation of 0. Now that tells us no rings, no double bonds, we just have a straight chain somewhere. So now let's jump back to the IR. We already deduced that there is an OH here because of just how noticeable it is. And that is going to be our primary functional group we're going to be working on. So now let's look at the proton NMR. We're given a whole lot of peaks. So let's start taking this one by one by making an integration table. Okay, we have a peak at 0.9 of integration of 6. We can assume that it's probably going to be a methyl group. We have an integration of around 1.5, 2 hydrogens. Integration of 1.7, 1 hydrogen. Integration of 2.7, 1 hydrogen. Integration of 3.6, 2 hydrogens. Now let's take a pause. Do all of the integrations, hydrogens, match up with our molecular formula, and if we add everything, we should get 12, and that makes sense, so we don't need to multiply anything by a factor. So now let's propose a reasonable resonance structure. Not resonance structure, reasonable structural components to make this molecular formula. So 6 hydrogens, we've done this a bazillion times. It's likely going to be 2 CH3s. This is going to be an N piece. We have 2 hydrogens here, likely going to be a CH2. This is going to be a mid piece. And now let's skip these hydrogens for now. Let's go to this 2 hydrogens, likely going to be a CH2. This is going to be a mid piece. And now we know for a fact that somewhere in our molecule we're going to have an alcohol. So it might be kind of confusing. Do I pick this one as the alcohol, the 1.7, or the 2.7 as the alcohol? But remember, for alcohols, we're only going to have a peak of 1. Okay? The other peak that has 1 hydrogen has a whole bunch of different peaks, and that's very indicative of a hydrocarbon group. So we already know that the group at integration frequency 2.7 is going to be the alcohol group, and that has to be an N group. And therefore, this group we've seen before is going to look like this, and this is going to be mid group. I'm going to go ahead and label this A, B, C, D, E. So now we have a bunch of proposed structures, and we have mid pieces and everything labeled. I'm going to go ahead and label this as well. A, B, C, D, E. Now, before we move on, let's look at the proton NMR. Sorry, the carbon NMR. 1, 2, 3, 4 peaks. 4 peaks. How many carbons do we have? 5 carbons. 4 is less than 5 in the molecular formula, and that should tell you plane of symmetry somewhere in our molecule. So now, let's start to assemble our structure. So we know we have the CH2s, or sorry, the CH3s at the around 0.9, and those are going to be chemically equivalent. So that must mean they must come off of the same carbon. And if we try to piece everything else here, as seen in previous examples, if we try putting a CH2 here, our structure dies. We can't really put an OH there, so the only thing that makes sense is putting a CH there. And now by process of elimination, we can't really put oxygen there because our structure dies, so the next couple groups has to be CH2 groups. Okay, and now let's go ahead and label this. This is all going to be A. This is going to be C. It's kind of strange. B is going to be either here or this one could be E. It's not really known if we don't look at the shift of the proton NMR. And this one is going to be D. So let's automatically rule out D because we know that has to be the alcohol group, so we don't need to worry about that too much. Now let's look at the methyl groups, group A. Group A, let's look at the methyls and look at its surrounding carbons. The surrounding carbon here has 1 hydrogen. According to the n+1 rule, 1 hydrogen plus 1 should give a doublet peak. Surely enough, we have a doublet peak at A. So that makes sense. Now let's look at C. Let's look at its neighbors. 3 hydrogens up here, 3 hydrogens down here, 2 hydrogens over here. 1, 2, 3, 4, 5, 6, 7, 8. Remember, n+1, so it's going to be 9. So we should expect to see 9 peaks at this C integration. And surely enough, we have a whole bunch of peaks. 1, 2, 3, 4, 5, 6, 7, 8, 9 tiny little peaks. So this makes sense. C and A are good. I'm going to go ahead and circle them. And we know D is also good. Now for B and C, let's see if this makes sense. For B, let's look here first. Let's look at its neighbors. Over here we have 2 hydrogens, 1 hydrogen over here. That's 3 hydrogens total, n+1 gives us a peak of a quartet. So if we look at B, surely enough, 1, 2, 3, 4, a quartet, and this makes sense. And now let's finally look at E. We don't really need to because of process of elimination, but just for the sake of learning, let's look here. Over here at E, we have a triplet peak. So we can expect to see a triplet here as well. So if we go this way, there's an oxygen here. It's in the way. We can't really count that. Let's go this way. We see 2 hydrogens on this carbon. Remember, n+1, 2 plus 1 should give a peak of 3. Surely enough, 1, 2, 3 peaks. This makes sense. All right. And another way to double check that is because this is so far down this way, it is close to the electronegative atom, which in this case is oxygen. So that also makes sense. As you can see, this is basically a whole big puzzle. But if you take everything very methodically, one step at a time, I'm sure you guys will be just fine. The previous video that I made saying you have to follow a certain number of steps, you don't necessarily have to do. Like for example, for compound C, I looked at the IR before I fully figured out the molecular formula, just because I know immediately, okay, we have an alcohol somewhere in here. And the same thing can be applied if you see a sharp peak at 1720 or something like that. All right, good luck on your guys' exams. I know this video was long. Hopefully you watched it at 2x speed, and if you didn't, I'm sorry. If you have any other questions, feel free to reach out to me. I'll be as available as possible. Thank you guys.